Good morning, student. This is the first lecture of transport phenomena subject. So, good morning, students. Today we are going to start a very basic fundamental course. Okay, a very basic fundamental course in chemical engineering, which is also relevant in several other disciplines. For example, in mechanical engineering, in biotechnology, and several such disciplines where we would get transport of momentum, mass, heat, and in many cases this process are coupled. Means some cases it will be mass and momentum, then some cases mass and momentum and heat. Okay. So in this case we are going to see how uh, this all mass, energy and momentum, uh, with these different process are interrelated, and whether or not uh, the approach of the heat and mass transfer can be provided within any framework of several governing differential equation and their solutions. So before we proceed, first we have to know what is the transport phenomena. Okay, so as I have mentioned that this is a very basic fundamental course in chemical engineering. Okay, so this is related with the transport of momentum, mass and heat, and the prerequisite of this course are the fluid mechanics, heat transfer and some portions of the mass transfer. Okay, so this introduction to mass transfer is preferable for this transport phenomena. So introduction of this mass transfer is preferable for this transport phenomena. So I would expect that every students have gone through the in the fluid mechanics subject the heat transfer as well as some introduction part of the mass transfer subjects. So these are the books which you can follow. So there are several books of the transport phenomena. So from my point of view, these are the books which can help you to proceed further to get the knowledge for this transport phenomena. So first one is the transport phenomena by Bart Stewart and Lightfoot. Second one is the transport phenomena fundamentals by J.L. Plosky. And third one is the transport phenomena approach by Professor K.S. Gandhi of IISc Bangalore. Okay. So I'm going to follow in which you would get the most information regarding this transport phenomena. Okay. Now, first, try to see what is the transport phenomena. First, try to see what is transport phenomena. What the exactly the transport phenomena is. So as I mentioned that the transport phenomena is basic fundamental subjects of the chemical engineering. So it is a fancy way that chemical engineers groups together the three areas which are the fluid mechanics, heat transfer and the mass transfer. Okay, so it groups together these three areas of study that have certain ideas in common. So transport phenomena are just a fancy way that chemical engineers group together these three areas: fluid mechanics, heat transfer and the mass transfer. So these three areas are the transport processes uh, of these transport phenomena subjects. So where we have some certain ideas in common. So why we need to study this transport phenomena? Because if we want to make a process equipment design, if you want to make a process equipment design, then we need to have the knowledge of chemical engineering, thermodynamics, as well as for the material science, process economics, chemical reaction kinematics, and the transport phenomena. So every process that has the phenomena of this transport process, which includes in those three areas, which are the heat transfer, mass transfer and fluid mechanics. Okay, so we need to study this transport phenomena. If we know this transport phenomena as well as all these uh, subjects which we need the knowledge, the basic things we need to know, so from these we would able to design a process equipment of any means any continuous process. Okay, so which is related to the chemical engineering or any subjects which is related to this transport phenomena. So what are the levels of analysis of this transport phenomena? So there are three levels which are macroscopic, microscopic and the molecular level of analysis. Okay. So macroscopic analysis is nothing but the macroscopic balances where we need to write down the balance equations and the equations which would describe the mass, momentum, energy and angular momentum within the system, which would describe the mass, momentum and energy and angular momentum within the system, and no need to understand the detail of the system. So in this macroscopic level of analysis of this transport phenomena, we need to write the balance equation, and where the in that equation where the mass, momentum, energy and the angular momentum is described, and no need to understand the details of the systems. Whereas in microscopic levels of analysis, the examination of fluid mixture in a small region within the equipment is required. Examination of fluid mixture in a small region within the equipment is required. And using this microscopic level of analysis, we can write down the equation of change that describe mass, energy and momentum and angular momentum change within the small region. So what is the aim of this microscopic analysis? Its aim is to get the information about the velocity, temperature, pressure and concentration profile within the system. So aim is to get the information about the velocity, temperature, pressure and concentration profile within the system. Next is the molecular analysis. So this molecular analysis mainly it seeks to a fundamental understanding of the mechanism of mass, momentum, energy and angular momentum in terms of molecular structure and intermolecular forces. In terms of molecular structure and intermolecular forces, as it is a molecular analysis. So it involves some theoretical physical and physical chemistry work. Okay, so it involves some theoretical physics and physical chemistry work. So there are three types of level of analysis of this transport phenomena. One is macroscopic, where the macroscopic balance is required and where no need to understand of the detail of the systems. And in the microscopic case, we need to the aim is to get the information about the velocity, temperature, pressure and the concentration profile of that system. And for the molecular system, we need to understand the mechanism of the mass, energy and momentum in terms of molecular structure and the intermolecular forces. Okay, so for that case, some theoretical and theoretical physics and physical chemistry works are needed. Next are the transport processes. So as I've mentioned, the three areas: the fluid mechanics, heat transfer and the mass transfer. So from the fluid mechanics, so we can say the momentum transport, the transport of momentum which occurs in moving media. Momentum transport is nothing but a transfer of momentum which occurs in moving media like the fluid flow, sedimentation, mixing, filtration, etc. And the heat transport, this is the transport of energy from one region to another. The example is the drying, evaporation, distillation, where we require this, where there is a transport of heat. And another is the mass transport, where the transfer of mass of various chemical species from one phase to another distinct phases are occurred. So the example of this mass transport is the distillation process, absorption process, adsorption process, etc. So these are the three transport processes in the transport phenomena. Those are momentum transport, which involves in the fluid flow, sedimentation, mixing, filtration, etc. And for the heat transport, which involves in the drying, evaporation, distillation. And the mass transport, where it involves also the distillation, absorption, adsorption. Okay. Now we try to see what is the transport phenomena. So for example, we have a flow of a fluid through a conduit. Okay, we have a flow of fluid through a conduit. So we should be able to derive an equation which would give us the relation between the pressure drop and flow rate of specific fluid through a conduit of known diameter. Okay, so we should able to derive an equation which would give us the relation between the pressure drop and the flow rate of specific fluid through that conduit of known diameter. So if the geometry is known, we should be able to model the fluid flow process in such a way that the fundamental equation, when integrated with appropriate boundary condition, that would give us the velocity distribution of the fluid inside the tube. Okay, so that fundamental equation, when we integrate with the appropriate boundary condition, it would give us the velocity distribution of the fluid inside that tube. That this velocity distribution is very important for this transport phenomena. Means this velocity distribution uh, means it is this velocity distribution is very important for this when we are deriving an equation of when there is a fluid flow through a conduit. Okay, now let's take the gradient of the velocity profile near the wall. So it can be used to calculate what are the force exerted by the solid. So what are the forces exerted by the solid on the fluid in the direction reverse to the flow? So whenever there is a flow, so there always be a reverse flow. Now what are the forces exerted by the fluid on the solid in the direction reverse to the flow? So when a fluid flows along any inclined plate, so when there is a fluid flow along any inclined plates, so there will be a forces or interactions between the liquid and the solid surface. So there will be a forces between the solid and liquid surface. So when the fluid flows along this inclined plate, there will also be the forces or interactions between this liquid and the solid surface, and this interaction is essentially governed by a property which is known as viscosity. This viscosity plays a very important role in the momentum balance of this transport phenomena. Okay, so this viscosity have a very important role in the transport phenomena for the case of momentum balance. So whenever we have the viscosity, whenever a fluid layer flows over another layer, there would be some interactions between the two layers. When there is a flow of fluid over another layer, there would be interactions between the two layers, one on top and one at the bottom, and as a result of which faster moving fluid would try to drag the slower moving fluid. Okay, so as a result of which, for the flowing of the layers of that fluid, one faster moving fluid would try to drag the slower moving fluid along with it, and as it move away from the faster moving layer, the velocity of the fluid layers will progressively decrease as it moves away from the faster moving layer, the velocity of the fluid layers will progressively decrease. So this is a unique process which is relevant in liquids to some extent, and it also present in gases, and uh, it also dictates how much pressure drop can be expected when a fluid flows through a pipe. It also dictates how much pressure drop can be expected when there is a fluid flow through a pipe. So when we think about heat transfer, we all know that heat transfer takes place whenever there is a difference in temperature. Whenever there is a difference in temperature between 2 points. Okay, whenever there is a heat transfer, uh, means whenever there is a difference in temperature between the 2 points. So if you think about heat conduction, then it is not the temperature in between the 2 points are important. Okay, whenever we are considering the heat conduction, so there is not the temperature is important in between the 2 points. The important is the distance. So important is the distance between the 2 points, that also plays a critical role in evaluating what is the total amount of heat transfer. What is the total amount of heat transfer? So it is not the temperature difference that is important. So it is the temperature gradient within that is important. Similarly, for the case of mass transfer, we would see that the total amount of mass transfer is done by the diffusive process, which is molecular in nature and would not depend only on the concentration difference of a species between the 2 points, but it would depends on the concentration gradient as well. So now these concepts are phenomenological concepts. So another advantage of trying to design or trying to develop the fundamental equation from the first principle is that many times with the emergence of new technologies, new areas and new applications, which we will come across situations where no fixed relations exist or even the correlations are not present. So for that case, if you would like to design something, or if we like to upgrade a laboratory process into pilot plant or beyond, the fundamental aspects of different process. Okay, now what is the important, whether the temperature difference is important for this case, or the temperature gradient, or is the velocity over which the hot fluid flows over the cold fluid surface is important, or which is the thermophysical properties are important. Can these properties be grouped together in order to obtain certain dimensionless groups or the similarity parameters that would tell us about the similar behavior of different fluids only if those numbers are the same? Okay, now what are the consequences of studying this transport phenomena? So it is not only understanding the process but also identifying the dimensionless groups, the number which are going to be important in deciding the amount of heat, mass and momentum transfer. Heat, mass and momentum transfer. So additionally, this dimensionless group would also tell us if these numbers are constant, then it is possible. If these numbers are constant, then it is possible. So the only thing we need to know is the appropriate dimensionless constant must be used for the heat, mass and momentum transfer. So if it is possible that the equation for, let's say, the mass transfer can be solved for a specific process using certain simplification, then we need to have to solve the heat transfer equation once again. So we simply use the relation that has been obtained for mass transfer as the relation for heat transfer. So if you simply substitute the dimensionless for the relevant to mass transfer by that of the heat transfer. Okay, So with all these initiations of new technologies, new areas, and the new concepts, a strong background of this transport finance process, which would always be compromised, which is always be comprised. So for all these process, how to scale up and go from the laboratory scale to the commercial production, an idea should have of the determining steps in terms of fundamental concepts as developed in this transport phenomena course. Okay. So with the advent of new technologies, new areas and new concepts, you would always like to have a strong background of this transport process, and for all these processes how to scale up and go from laboratory scale to the commercial production, and we need to have an idea of the determining steps in terms of fundamental concepts as developed in this transport phenomena course. Now fundamental concepts of this momentum transfer. So fundamental concepts that of this momentum transfer that we already knew through the fluid mechanics, that when we are going to talk about the new concepts, which is the shell balance, it is essentially a force balance method that we are going to see in this, how this shell balance can lead to the governing equation for any case. And for momentum transfer, what are the relevant boundary conditions? Okay. And for the momentum transfer, what are the relevant boundary conditions? So the shell balance can lead us to the governing equation for the case, and for the momentum transfer, what are the relevant boundary conditions one would expect in the case of fluid flow or the momentum transfer. So the formation and solution of momentum transfer in laminar flow we would see, and then it would automatically be apparent that many of these process of many of these processes can be handled by a simple shell balance, which is very simple in nature, which is very simple in nature. So whenever there is a geometry slightly complicated, we would probably like to have more generalized approach, and the shell balance methods cannot be used in that case. So one of the generalized methods of analyzing any momentum transfer comes from the application of Newton's second law for open systems. Newton's second law of open systems. Okay. Now this Newton's second law for open systems, that should give us an equation which is known as the equation of motion, or in more common terms it is known as the Navier-Stokes equation, or it more commonly known as the Navier-Stokes equation. Now this Navier-Stokes equation is a very powerful tool which can be applied in the momentum transfer, and it is a very long equation, but in many cases by simply using the geometrical constants, by considering the geometrical constants, or the understanding of the length scales, we would be able to discard many of the terms in the Navier-Stokes equations. Then it will be more simplify simplifying form of that different means the Navier-Stokes equation, and which would give us a very compact differential equation to solve within the appropriate boundary condition, giving to rise to fundamentally what is the velocity distribution. What is the velocity distribution? So this approach is also known as the differential approach. So this approach is known as the differential approach. So this differential approach is important, but there is another approach which is known as the integral approach, where there is another approach, that is the integral approach, and we will walk about that well, where we are not interested in what happens at every point in the flow field, but what happens on the average basis. So we are looking for what is the average velocity, not the point velocity in the integral approach. Okay, so we are looking for only the average velocity, not only the point velocity. Now for Example, conduction, convection, and in a system it is possible that there may be a heat generation. So it could be a, if it let's take a example for a nuclear reactor model, where we can see that there will be a heat generation term. In the nuclear reactor model there would be a heat generation term, and there could be the fluid which is probably flowing at a very high velocity. So as there is a high velocity, so the layers of the fluid will flow past each other with different, means with different sufficiently high relative velocity, such that there would be the frictions between the liquid layer exactly same as the between two solid surfaces. So and these frictions will give rise to some heat generation. So heat generation by external forces, by external sources, or by the flow of fluids, or by flowing past each other, the work done by the system or the work done on the system, all these will continue different terms of the energy equation. So we will derive and we will discuss simply and solve the energy equation with relevant boundary conditions. So again, the goal is to obtain the temperature field, temperature at every point in the field, which we can then be used to derive quantities of engineering importance, such as what is the convective heat transfer coefficient, okay, such as what is the convective heat transfer coefficients. So the same can be done for the mass transfer also. The same can be done for the mass transfer also, but in the case of laminar flow. And we will use the equation in Navier-Stokes equation, or the energy equation. So the species balance equation, which is nothing but the mass balance equation, and the equation of continuity, the conservation of heat and mass transfer. And towards the second part of this course, we will introduce a very important concept which is known as the boundary layer concepts. All these transport processes that we are talking about, that would takes place in a region very close to the interface, so if we are thinking about the heat transfer and the liquid is in contact with a solid, the most of the heat transfer between the liquid and the solid takes place in a layer which is very close to the solid surface. So across the interface, the temperature change rapidly from the wall temperature to a temperature which is more or less remains constant for throughout the body of the fluid. So this region in which the temperature essentially drops from that of the wall to that of the liquid, which is more or less remains constant, the region is known as the boundary layer. The region where the temperature is essentially drop is known as the boundary layer. Okay, so the same concept is valid when a fluid layer moves over a solid layer. Then it can be shown that the velocity of the fluid which is moving on the stationary plate, it varies from a value equal to 0 to the value to the free stream velocity. So the velocity of the fluid which is moving on the stationary plate, that varies from a value from 0 to a value equal to the free stream velocity, that is at the interface where there is a air and liquid. Okay, so the velocity of the bulk air moving above the plate in a region which is very close to the solid surface. So this thin layer in which the velocity, the temperature or the species concentration changes from its value is known as the boundary layer. So this thin layer in which the velocity or the temperature or the species concentration changes from its value, so it is known as the boundary layer. This boundary layer having immense uses, fundamentally, conceptually, as well as in terms of deriving equations for heat, mass and momentum transfer between a solid and liquid surface when there is a relative motion. So whenever we are conceptually or the fundamentally deriving an equation for the heat, mass and the momentum transfer between the solid and liquid surface, so there is a relative motion, and there is a difference in temperature, and there is a difference in concentration of one of the species on the surface and in the liquid. So these three will be valid for the heat, mass and the momentum transfer. So there is a relative motion, okay, so there is a difference in temperature, or there is a difference in concentration of one species on the surface and in the liquid. Now the boundary layer thickness. Now what is the boundary layer thickness? It is nothing but the behavior of the heat, mass and momentum transfer in the thin boundary layer, and the science which is involved in this transport process are the part of this course. Okay, so the boundary layer thickness, where the boundary layer starts to form, from that region to the free stream velocity. So this region is called the boundary layer thickness. So some cases of the solution boundary layer equations, that would be a simplified if we use the integral approach. If we use the integral approach, okay. Now in some cases the solution of boundary layer equation would be simplified if you use the integral approach. So there is something called a momentum integral equation, when we would see, which would extensively use for the solution of turbulent flows or the turbulent boundary layers, and it also leads to as associated part which is like what is going to be the drag, So when the fluid flows over an immersed body, there will be a force experienced by the immersed body, which is commonly known as drag. Now, how to measure the drag? So, how to reduce the drag? How to predict the drag? This is the important things. So as we know, the drag means whatever the force experienced by the immersed body, which is commonly known as the drag, and in any application where there is a moving part, there would be some force exerted by the surrounding fluid on the moving part. Okay, so this force is called as the drag, and the fundamental problem is how to measure the drag, or how to reduce the drag, or how to predict the drag. Now the fundamental expressions or the fundamental concepts which can be explained by the boundary layers, and how that can give rise to the situation where it will be possible to model such processes. Fundamental expression which is coming from the fundamental concepts, and these expressions will come from the governing equations that we considered here in this transport phenomena for the steady state case. So the governing case means by implying the governing equation and the appropriate boundary conditions, okay, we would get the exact governing equation, uh, the equations of the velocity profile for the momentum transfer. Okay, so the fundamental expression and the fundamental concepts which can be explained by the boundary layers, and how that can give rise to the situation where it will be possible to model such processes. Now the objective. What is the objective of this transport phenomena? So the objective is to explain the heat, mass and the momentum transfer. The objective is to explain the heat, mass and momentum transfer by same type of equation, or by same sort of an analogy, which would tell us that under this specific condition it is sufficient to have an idea of the heat transfer mechanism that are taking place. So if we would like to know what is going to be the corresponding mass transfer equation for same situation, we need not to have to derive it once again. So if we like to know what is going on to be the corresponding mass transfer equation for the same situation. We need not derive it once again. The expression that we have obtained for the heat transfer can be used as the expression for mass transfer. Okay. So what is the mathematical basis of these statements? What is the mathematical basis of this statement? That is, please, the expressions that we have obtained for the heat transfer can be expressed as the expression can be used as the expression for the mass transfer. Now, the when these different transport processes are relevant such that one solution can be used for the other type of transport processes as well. So these analogies are extremely powerful tool because in many real life applications, and we would see uh, across the situation where it would be extremely difficult to conduct experiments and develop a relation and then do another set of experiments and try to develop another set of expressions for. Okay, now if it is possible to do heat transfer experiments, that is very easy to do, but it difficult to do the mass transfer experiment. So if we do not perform the mass transfer experiments at all, so we take the system in such a way that these two systems are geometrically similar, and we ensure based on our knowledge that we have gathered in this course that we would have to do in order to make the mass transfer process equivalent to heat transfer situation. So if we can make these two things equivalent, we do not need to work with the complicated mass transfer experiments anymore. So we do all our experiments on the heat transfer, which is easy to do, and derive relation and then simply project these relations for the mass transfer case that we have not done any experiment on. Okay, so only if we know the heat transfer expressions, based on that we can get the mass transfer parameters also, but we have to consider it that the two cases are equivalent. Okay, so we these two cases are equivalent and we do not need to work with the complicated mass transfer experiments anymore. So these similarities between heat, mass and momentum transfer is extremely powerful tool for practicing engineers as well as for scientists to predict what would be the transport process, and that would be the quantity of heat transfer or the mass transfer or the momentum transfer. If you know what is going on uh, to the system and what is the amount of the transport in any one of these process, so these are the there are the hundreds of different types of situations one can encounter. One will encounter in this case where these processes are coupled. So these coupled transport processes mathematically be difficult to handle because they would give rise to differential equation which depend on each other, and 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 a comprehensive solution of those cases in many of the situation would be extremely difficult. Okay, so the coupled transport process are mathematically very difficult to handle, and because it would give rise to a differential equation which depend on each other and comprehensive solution of those cases in many of the situations which would be extremely difficult. So these analogies give us a powerful tool to analyze, to understand and to obtain the results, to obtain the results. Now, starting with the very fundamental transport phenomena modeling, type of the cases where the shell balance we able to use to obtain the difference equation from a difference equation to a differential equation. We need to identify the boundary conditions and then solve the differential equation with the boundary conditions and obtain the expressions of the velocity. Okay, so this transport phenomena is nothing but the fundamental process of the modeling and the types of these cases where the shell balance would be able to obtain the difference equation, and from that difference equation, from the difference equation to a differential equation. Okay, and the boundary condition need to be identified. What are the boundary conditions involved in that systems? Means in the solid liquid interface or in the air liquid interface. Okay, so as I have mentioned, there should not be any relative motion in the boundaries. Okay, so for the momentum transfer there should not be any relative motions. So this is considered as a no slip conditions, or there is another boundary conditions we can say it is this in the in the air, liquid air interface, that is called uh, the no shear boundary conditions. Okay, so there is no shear in between the liquid and gas interface. So first we identify the shell, then making the shell balance we would able to obtain the difference equation, and from that difference equation we would able to find the differential equation, and from that boundary conditions we need to be identified, and taking and by simplifying that differential equation, and by integrating it we can get or solve the differential equation and obtain the expression of the velocity. So this is for the case of only the momentum transfer. So similar things can be done for the heat transfer and the mass transfer also. Okay, so this is the basic concepts of the transport phenomena. Okay, so as I've mentioned, there is a macroscopic, microscopic and the molecular level of analysis for this transport phenomena. So when we want to design any process equipment, so we need to have the concepts, all the transport phenomena. Now in this transport phenomena, so for the there are three areas: fluid mechanics, which is we will describe for the momentum transport case, and there is a heat transfer transport process, and there is another whom is the mass transfer process. So if we know the what are the phenomena going on in the system, if we know the conservations law, by using the conservations law, means for the transport phenomena we have that the rate of momentum in minus rate of momentum out equals to plus summation of the forces which is acting on the system will be equals to 0. Okay, summation of forces which is acting on the system will be 0. So in the next class we will describe more in about for the momentum transfer, where the viscosity plays a very important role, and simultaneously after the momentum transfer, finishing the momentum transfer, we will describe the heat transfer and then the mass transfer also. Okay. Thank you for your attention, students. So that's all for this first lecture. I think you would able to understand what is the basic things of this transport phenomena. Okay, thank you.